atomic clock broadcast is in.
It would have to be a fairly low frequency.
Yeah,
right?
it's a short wave. It's a short wave frequency, and it's broadcast from Colorado, I think. That's where the atomic clock is kept. And
Why? Because they're high. Wow.
I don't know. Well, short wave is interesting because it bounces, in the atmosphere and the ground.
So, does the atomic clock calibrate the latency, depending on where you are? Or?
I do not think so because this is actually getting the signal directly from the atomic clock itself, and the transmission time, in terms of light speed from that kind of distance is negligible. We're not talking about from Earth to Sun or something like that, which is about 8 minutes, I think. So it's good. Yeah. All right, so let's go ahead and get started. I'm pretty sure the recording is on. I'll double check. All right, it is on. Remember at the beginning of the semester, I mentioned that I will give you the solution of the homework assignments, and I will for this one, but I'm going to move it to the lab time. Okay, this is the one thing that took up a lot of lecture time in all of my previous classes. So I'm going to move that part to the lab time. So I will basically do the whole program right in front of your eyes, including all the bloopers and whatnot. So you guys get to enjoy. You get the same problem that I did. So you get to enjoy that part too.
And will you be posting that one on?
Yes, when it will be recorded, and unless I have technical difficulties, it will be recorded and posted on YouTube as well. But if you make it to the lab, you can ask questions, okay? Because if my approach is not the same as yours, and you have a question about this part here, you can certainly go to the lab, and then we can have a little discussion as well. Okay, so I think it will be good. So as far as the class topics are concerned, we are moving forward, and we are going to spend a little bit of time to talk about non-number representation, and then we'll move on to the next topic, which is actually what I have been waiting for since the beginning of this entire class. Okay, because that's the stuff that I'm really familiar with. This is all new stuff to me too. All right, so getting to non-number representation, and what I'm supposed to talk about would be character code and graphical data. And for all of these, I don't really think it's going to be a lot of time. How many people do not know what is ASCII? Which is okay. I'm just asking the question because you may not have that exposure in cisp 360. So if you do not have any exposure to ASCII code in cisp 360, let me know. I think I did. I think I talked about that. Without just talking about that, well, you never know. And some people may not have taken cisp 360 either. Okay, so I just want to make sure I cover all the bases. No questions about that? Okay, so we can talk about something more obscure than ASCII then. Which is based on the same concept, okay? This is actually, this precedes ASCII, okay? So people were using this before ASCII, and it's called ABCDIC. ABCDIC, I think, okay? Google, correct my spelling. There we go, ABCDIC. Okay, so ABCDIC stands for, okay, let's see. Oh, well, it's right there. Extended Binary Coded Decimal Interchange Code, which is a really long name for something that is kind of obscure. But IBM came up with this first, okay? Now, if you remember the original purpose of computers, it was not, well, a lot of computers were not used for storing addresses and stuff like that. They were purely used for calculations. And that was definitely the case with IBM computers. Okay, IBM mainframes, particularly, were used by financial institutions, okay, banks, governments, and whatnot, to crunch numbers, basically, to keep track of accounts, balances, and stuff like that. So to IBM, it is far more important to represent numbers exactly and do all the calculations than let's store addresses, okay, names, and stuff like that. That was not really as important to IBM. So we'll start with the discussion of what is binary coded decimal, which by today's standards seems like that's not very smart. but it was smart from a certain perspective. Binary coded decimal is like this. So I'm going to illustrate it using mousepad here. And you can certainly search in Wikipedia and find that as well. So it's just binary coded decimal, and you can see that there's right there, binary coded decimal. Okay. So the whole idea of binary coded decimal, and since Wikipedia has it, I'm not going to write anything about it. Now, that's the whole idea of open source, right? If somebody has it, I'm just going to use it. Okay. So binary coded decimal is basically just saying I will use a certain number of bits to represent the digits from 0, but only up to 9. Okay, it is not hexadecimal. It is really just decimal. But it's decimal using binary coding, which means 0 is represented by 0, 0, 0, 0, 1 is 0, 0, 0, 1, and so on, and 9, not surprisingly, is represented by 1, 0, 0, 1. Which is also how you code 9, the value, in hexadecimal. But the rest of the bit patterns are not used. Okay, at least they're not used to represent digits. So from 1, 0, 1, 0, all the way to 1, 1, 1, 1, they are basically just not used. So we have 6 combinations out of 16 not being really utilized. Okay. So why do we want to do something like this? In other words, if I want to represent 100, okay, the value of 100, I would be representing it as 0, 0, 0, 1, which is 1, 0, 0, 0, 0, which is 0,
Also,
0, 0, 0, 0, which is also 0.
Like a positional notation. There's a positional notation.
This is
Like positional, so like in our decimal where that 1 represents 10 to the its
correct,
position.
yes. So this is, so the least significant nibble, 4 bits, is representing how many ones we have. The next one is how many tens we have, not 16s. And the next one is how many hundreds, not 16 squared.
Did you
Okay?
call it a nibble?
Nibble.
Okay, that's a
Yeah, 'cause it's
N-I-B-B-L-E.
like-
oh.
Yep, it's somewhere between a bit and a byte.
Well, I was wondering if that's like official, because I know that we do
It is
flops
official.
as well.
It is
Nibble
official.
flops and bits. Okay.
Yep, it is official. But people usually don't refer to it as a nibble for whatever reason.
Because it sounds silly.
It sounds silly.
I mean-
Especially when YouTube does the transcription, it might come out a little bit strange.
Yeah, it might be.
Yeah.
You start throwing
Okay, but anyway, this is binary coded decimal, okay? It's not hexadecimal. Now, why would IBM do something like this instead of just saying, oh, why don't we just represent everything in binary? Because that's what we have been dealing with, right? Everything is represented in just plain binary. This is not binary, and yet it's not ASCII code, it is binary coded decimal. Well, the main reason has to do with IBM has to be able to represent numbers exactly, okay? So they were using fixed point numbers by having an implicit point somewhere, like here. So now they can represent, currency all the way down to, a cent, okay? Assuming this is $1. And they can basically keep track of, bank accounts and do all kinds of calculations like interest rate and whatnot, exactly, or at least, to a certain specification. And this is also used, at a very, very a long time ago, and that's before computers became the way they are now. Floating point number calculations would take a lot of time. Except with this, it is actually a fairly efficient way of doing things without having to rely on floating point calculations. Okay, so this is binary coded decimal, and if you read the rest of it, it will give you pretty much the same content. And then later on, IBM had to deal with representing, in addition to digits and numbers and values, they also have to deal with letters and punctuations and whatnot. And that's when they came up with ABCDIC. So when you look through ABCDIC and code page layout, this is how ABCDIC is done. This part here, when you look at the rows, each row is representing 16 code that shares the same most significant 4 bits. And then when you look at the columns, each one is basically one value with the same most significant formulas. So I'll just pick you one example. It's really weird in a certain way because some of these code is not used, and then when you look at A to Z, it is not contiguous. So this is the code for A, this is the code for B, and when you look at I and J, they are not contiguous. I is represented by 137 in base 10, and then J is represented by 145 in base 10, and they are not right next to each other.
Numbers in between little blocks. How many you said we had 11 bits that weren't used for every nibble? So you got to do something with it.
Well, it's not because of that, but if you look at how many positions are actually in use, it's 1, 2, 3, 4, 5. There are 9 in use on each row, which is kind of odd. Okay, I really do not have any idea why they code it this way. I just know that it is an inefficient way of coding, from letter punctuations to binary code.
And efficient or
Inefficient. It is not efficient. Yeah, because we have a lot of gray blocks here that are basically not used. And it does use up the entire code table. So there are 256 entries, of which there is a lot of gray area, which means it's not used. Yep.
As far as the timeline, is this like Unicode or?
This is pre-ASCII, and ASCII is pre-Unicode. So when you look at the history of this, it is devised in 1964, and that's even before I was born. So that's ancient, double ancient, maybe double ancient. Yeah. Yeah.
IEEE?
1964, that's even before 2010, 2001 A Space Odyssey was made. Okay, and that's a pretty old movie, and people who watch that movie would know that the computer name is HAL 9000, but if you look at HAL and IBM, do you see any relationship? This is one letter from H, this is one letter from A, this is one letter from L. Yep.
Like, I think I remember there's a picture with a control console with like an IBM logo on it.
Something that looks like an IBM logo. Yeah, probably not exactly the IBM logo. And this is back in a time when movie makers do not try to make money by advertising certain brands. I'm pretty sure you have watched science fictions with futuristic Lexus, futuristic Audis, and so on and so forth. Or you watch The Matrix, right? And the good guys are always driving not Cadillacs, but they're also always driving some kind of GM. And the cars that get blown up, they're always Toyotas. In case you haven't noticed, the number of Camrys that got blown up in that movie, or Fords for that matter. And I think the first movie that did this, the very first movie that set this particular trend was RoboCop. Okay, if you just count the number of Fords in that movie, that's a advertising thing. But back in those days, they do not do anything like that because I guess they never came up with the idea, or they did not, or for whatever reason, the author may not like IBM and just say, okay, we'll just play with that name but not use it. But this is a really old standard. Okay, this is a really, really old standard. But the bottom line is, as odd as it is, okay, so let's go back to the.
2001: A Space Odyssey.
Yep, it's a great movie. So as odd as this is, let me go back to the code page here. It's okay as long as the devices understand exactly the same standard. Particularly the terminal and the mainframe computer, if they understand the same standard, no problem, right? Things will still get displayed correctly. Between the printer and the mainframe computer, same thing. Okay, as long as they understand the same standard, it will still be okay. So ASCII, which is American Standard Code for Information Interchange, came along a little bit later. So we'll go look it up. And this is the code page for ASCII, and we'll look up the history. Well, actually, work on the standard began before ABCDIC, and it was published at about the same time as AppSync. Major revision in 1967, which is when the movie 2001: The Space Odyssey was filmed, because it was released in 1968. And the most recent update is 1986, which is actually fairly recent if you think about it. Okay? But if you look at the code page, which is really easy in this one, because you just have to go open up a terminal in any type of Linux machine and just type man ASCII, and that will give you pretty much everything that you need to know, because that's the whole table. Okay, and it makes more sense because you don't see all the gray blocks. From A to Z is one contiguous block. Uppercase is one block. Lowercase is one block. 0 to 9 would be 2, 0, all the way up to 9 for 0 to 9. And then we have the control characters occupying the first 27, code. So control D, for instance, is code number 4. Okay, control C is number 3. Line feed is number 10, and so on and so forth. So this is a much more logical way to lay out the coding of whatever you need to send to a printer or a terminal. Yep.
But for today's uses, like stuff like end of transmission, still used, or is that much more like probably networking?
Yes, in networking, a lot of those are still in use, especially when you look at transmission protocols. They're still in use. Yep, because they're really old standards and they're just over there. Some of these are actually used in text files, right? If you look up, new line, is still used. The bell signal is actually still used. If you send a bell to a terminal, it would actually ding. It would actually give you a ding. But in the good old days, it's an actual bell inside the device, and there's a striker to make it sound ding like that. Yep. All right. So, are there any questions about the ASCII table, or why we have ASCII encoding? Well, the only purpose is for the mainframe computer, terminals, printers, and other computers to be able to share information. That's the bottom line, okay? We need to have one single standard so that the same bit pattern is representing the same thing. That's basically it. Are there any questions about the ASCII table or the AppSync table? No questions? All right. But the ASCII table obviously is, well, as the name implies, okay, it's only intended to be used in which region of the world? Pretty much in the United States, right? Pretty much in the United States. And that was not a bad assumption in the 80s or the 70s, but these days, that would not be a very good assumption, right? So that's why the ASCII table is still used, okay? It is still used a lot, especially with coding, okay? All your C and C++ files, source files, they're all encoded in ASCII. But what about, all the websites, the international websites, okay? So I can show you an example, just so that we know what we're talking about here. So, exactly, okay? So I'll look up, I don't know.
Just ASCII 2? Isn't it just ASCII 2? ASCII 2? Isn't it just
No, it's not ASCII. It's actually
Unicode.
called
Unicode?
Unicode. Yep. But I want to show you, why it is a necessity. Okay. So we'll go with. Well, Gundam is actually not a very good example because it is highly westernized. Okay, it's not one of those things where you find a lot of kanji. A better one would be probably Bleach. Would be a better one. But anyway, but when you look at just the wiki page here, you can see certain characters are not, in English, right? Okay. So if you look at this part here, this is it's kind of it is the pronunciation-based characters in Japanese. Okay, so they can basically borrow words from all kinds of foreign languages because they can approximate the pronunciation of those words.
With the kind of phonetic limits, but
Right, it has limitations, but they can still do a certain amount of approximation. Like the way they say computer is kind of the approximation of computers.
Well, that's why that's so.
Yeah, that's why when they also when they pronounce Western names, a lot of times they have to add something to it because there's no direct mapping to the consonants. Okay, so they always have to map it to a character that does not have just the consonant but also a vowel, attached to the consonant.
like certain sounds like TH don't exist.
There's absolutely no TH, either TH
Yeah,
does
like
not
L
exist.
and R interchangeable.
Yep. but the point is, what about this character here? Okay, how does the browser display this character, and how is it actually encoded? What is being transmitted from the wiki website to this browser in order for that character to get transmitted? That is the question. Okay, it's Unicode. Okay, now Unicode is 16-bit wide, which gives it 65,536 unique combinations. ASCII occupies one of the pages, the first page of Unicode. Okay, so it uses up 2/55 of all the code pages. I think Chinese characters may use up a few thousand at the most. Okay. I think in order to be able to just do everything in a normal daily life, I think people need to know what 500-ish characters. Which is not really a whole lot. I mean, if you think about it, 500 characters will get you around on a daily basis, like taking a bus, go somewhere, look up the price of something and stuff like that. And most people know about 1,000 to 2,000 to read newspaper and stuff like that. Okay, so 4,000 includes a lot of stuff already. But Unicode is not limited only to all of these kind of Asian languages. If you look up any type of known language on Earth, Unicode covers it, and it goes beyond that too. Okay, because I believe Klingon is actually in Unicode as well. Some of you look at me and go like, nah, that's you're just pulling my leg here.
It's recognized by the United States government as it, so.
We don't buy it.
So we'll verify that, right? Yeah, Klingon Unicode. That it doesn't show that. Oh, okay, maybe this page has it. So I'll go here and then we'll look up a Klingon. And we'll see whether the characters are displayed here. Do we see any characters? Okay.
Well, actually, yeah, there's an entire Hamlet has been transcribed into Hamlet's been transcribed into
Klingon
well, ever
alphabet.
since it
There we
was
go.
mentioned in the 6th movie, it's being
There we go.
originally-
So it depends on whether you have the font set installed on this computer, and if you don't have the font set installed, obviously it's not going to render correctly. Sorry.
Is that Unicode range?
Unicode range is F8D0 to F8FF. So not really a lot. I mean, that alphabet is fairly, simple because from D, which is 13, all the way to 16. So there are only 48 unique code characters in Klingon.
More
I mean, that's more than English.
Well,
They probably
maybe
include
uppercase
punctuations and stuff like that.
Oh.
Uppercase, lowercase,
Oh.
angry words versus not so angry words.
No such.
Dying words versus angry words. I think that's probably an appropriate distinction in Klingon. Today's a good day to die as opposed to I am dying. Right now. Yeah, but isn't that interesting? That even Klingon gets a page in Unicode. Okay, and it's 16-bit wide. Most C compilers do not understand Unicode at all. So forget about writing a C program using Klingon variables. Okay, it's not going to work. We tried that many years ago. The company that I worked for was trying to port our compiler not to Klingon but to Japanese. Okay, to Japanese only. and we came this close of being able to let people write programs with variables written in Japanese characters.
So when you say, are you specifically using variables to say like the language keywords will still be in English?
Right. Yep. So you can only have variables or function names in in Japanese in that case, but I don't think GCC or C99 accepts anything other than ASCII as in a source code.
Would it be? Because I've always thought about like how English in like America per se has kind of like a monopoly on programming for the most part. Because most of like other places where you go, you're only substituting in variables and you can't actually change the keywords. Is it possible, or is it like somebody else has to write it, or?
I do not know. I really do not know the answer to that question. All right. So are there any questions about Unicode other than, where do I download the Klingon font set? Because I know some of you are doing it right now on your phone. It's like, I want to download that font set on my phone.
I want my C code.
Well, this makes me wonder, how many, fictional, languages, is actually in Unicode. Is Klingon the only one, or do they also have ones for other type of fictional languages? What do you mean with fictional?
Unicode range.
Hmm?
Unicode range.
Unicode range.
I mean, and it'll probably also be like, figure out what demographic would be interested enough to.
That is true, but I think, if they can put pretty much the entire set of Chinese characters into Unicode, I think that really says it all. I mean, and I think that there's a different Unicode for the simplified version as opposed to the traditional version. And I think you may know better. Is that true? So the same for the same character, the simplified version and the traditional version has different Unicode.
As I remember, as long as you install apply this together, it's both are fine. But normally we suggest you use a simplified.
Okay.
Yeah. So we use for the conversion.
Okay. I can look it up really quickly. Simplified traditional. Because I want to see whether it is possible to display both on the screen at the same time. Okay, that's just a bitmap. It doesn't count. Okay, and it is possible. I just saw that part. Okay, I'm gonna point out which part here. These three are in simplified version, and these three are traditional. And each one has probably 3,000 to 4,000. Okay. But when you think about it, 3,000 to 4,000 out of 65,000 is still not really a whole lot, okay? And that really shows you, the extendability of Unicode as opposed to ASCII, which only gives you about 255 possible combinations.
What 256?
You need Martian.
Where's the 256 go? Where is the 256?
Oh, 256 combinations, that's correct. Go ahead.
Just joking, I said you need Martian or something to fill that up.
For Martian? I would want to see Vorlon. Yeah, from Babylon 5.
Oh yeah, there you go. Probably one thing for those.
They have some really weird, wiggly lines. I actually have the font set installed on my home computer.
What about the Cyclone?
That's how he writes ours.
Cylon. All right.
Letters and just the shapes of the sound.
So are there any questions about Unicode, non-number representation? I think we're done with character codes. It's really just just a standard, okay? From a computer to another computer, they just have to understand this means the same thing. That's all. Okay. Graphical data or audio data and stuff like that is actually number. It is a number representation, because when you look at a single pixel on the screen, it is usually represented by the RGB components. Okay. Now you can also factor in alpha, which is transparency, and also gamma, which is the non-linear characteristic of how we perceive intensity. Okay, so all of these, can be encoded into a graphics file and be transmitted from one computer to another computer. Okay, the standard, using the standard RGB representation is most standard use only 8-bit, or 8 bits for R, 8 bits for G, and 8 bits for RG and B. Okay, so that gives you about what? 16. Yeah, it gives you about 16 million. 16 million only colors. Okay, 16 million possible colors. Because if you think about it, we have 2 to the power of 8 plus 8 plus 8, right? 8 for R, G, and B. Okay, so that gives you 2 to the power of 24. But 2 to the power of 10 is about 1,000. So this is about 16,000. I mean 16 million unique colors. The interesting part, this is just a side note. Okay, the interesting part is there's a good chunk of color that we can perceive and differentiate that cannot be encoded into RGB. Okay, so if you ask any photographer, they can talk to you about your color space and how the monitor color space is not even close to the color space that your eyes can perceive. Most of the colors that cannot be represented using RGB on the monitor, I think they're on usually at the green/blue region, where your eyes can see the difference. Like if I give you 2 shades, your eyes can tell and say, oh, they're different, but they cannot be encoded onto a computer because
16-bit. Then they're 16-bit.
It cannot be represented using that. It's out of the gamut of RGB representation.
But it can be printed.
It can be printed if you have the right type of printer. Your camera also needs to have special sensors, because you cannot use the traditional RGB sensor to see that entire color space.
Yeah.
Yep. So it gets kind of interesting because the way we perceive color is not, the retina doesn't have exactly RGB pixels. So the way we perceive color is not the same thing as an artificial device like a camera. But that's kind of like a side note. When I took a lot of pictures, I kind of studied the color space thing a little bit. It's actually pretty complex. Okay, it's a really sorry.
It's like there's lab, there's CMYK.
Yep, and you can be very picky about it. And you have to calibrate your scanners, your monitors, and everything else to show colors as truly as it possibly can. And there will still be colors that cannot be shown on a regular monitor.
Yeah.
Yep. And then you have to pay lots of money for those monitors too. They're not just regular, monitors that we buy.
Like a $3,000.
Yep.
Is that the idea behind like higher definition?
Higher definition only has to do with pixels. I think the basic display is still RGB, but most people don't really care because they don't really need to look at the actual true color when you're watching a movie, especially when the whole movie is loaded with CGI and eye candy.
Are they like IOP or IPL monitors? Monitors that can display higher range.
Maybe the word to look for those of you who are interested in this sort of thing is look into color gamut. How do you spell gamut? Okay, spell check. There we go. Yeah. So this, if you look at any one of these pictures, it shows you, quite clearly what we can deal with, and what a computer can display. I think this one is good.
Just go to open image.
Okay.
Oh, yours.
That's fancy.
Right.
Google Tech, yeah. Google Tech.
Just go to open image in the new tab.
Okay. I just closed it. But that's okay. Okay. So the idea is, there's a picture that looks like this, and there's a triangle in it. The triangle is the space where the color can be rendered on a regular RGB monitor or can be encoded into just RGB. Anything outside of it would be things that you cannot see on a monitor. And typically they cannot be encoded by a camera either, because your camera only sees things in RGB as well. So there you go, a little bit of the history of color encoding. Even though it is mostly just numbers, the way we do it right now, the convention has limitations. Same thing with sound. Okay, when you look at sound, so we're kind of looking at graphical data. But with sound, it's a little bit different because it is the intensity of air pressure. Okay, and that can easily be encoded using just unsigned integers or regular integers. It's just a number of bits that you have to allocate to get the highest fidelity. Most people cannot differentiate anything more than 16-bit. So if each sample is a 16-bit sample, and the sampling rate is about 44 kilohertz, most people cannot tell the difference from the quote-unquote standard. That's a CD standard. So if you sample any faster or with higher resolution, most people cannot tell the difference. So that's pretty much the sensitivity of our ears. Even trained musicians cannot tell. I think 18 bits is the limit, and equipment can record up to 20 bits per sample, and that's about it.
And I think that's why MP3 works so well, because it's actually set at that level, so that you can compress it down. Like the actual original file may be really, really wide in its bandwidth, but you only hear this anyway, so we'll just chop it down.
Well, MP3 has a very interesting way of compressing. It uses the same concept as a FFT or fast Fourier transform. It actually encodes audio signal from what we call the time domain into the frequency domain. And they use that idea, because when you look at any sound, okay, you can express it as a combination of frequencies, okay, and that's the basic principle behind MP3. Is they just take a look at the sound that you want to encode, and it identifies the intensity of each frequency, and they encode that instead of the actual waveform. But it's lossless. It's lossy. Okay, it's not lossless. It is lossy because when you try to go for a, let's say, 64 kilobits per second encryption, encoding instead of 128 kilobits per second, you are basically reducing the number of samples in the frequency domain to approximate the original sound, and that's why things can sound really bad when you're trying to encode something that is complex to begin with. Like the sound of a real violin has a lot of nuances to it, but when you use like 128 or 64 kilobits per second encoding, a lot of the nuances is gone because they're missing all of these little fine points. On the other hand, if you're trying to record, let's say, just a pure sine wave, I would assume that even 32 kilobits per second would be almost a perfect render of the original sound, because it is so simple to begin with. It only has one component of the frequency domain.
So if you listen to techno music, it's compress it more.
Sorry?
So if you listen to techno music, you can compress it more.
Techno music, interesting, is also complex, because the techno, the synthesizers, have all sorts of ways to create complex waveforms.
As complex as you make it.
Mm-hmm. Yep. If you want, easy compression, you will just be looking at very simple
Bass.
Bass, a bell, for instance. That's a very simple waveform. But anything that is complex, would lose some kind of fidelity when you use MP3.
Yeah, but you lose the sound below the frequency you can hear, but you can still feel.
Right. Well, that's only with the proper speakers.
Yeah.
And the proper amp to
Yeah,
to feed it.
But there are sounds you can't hear, but you can feel.
Yep. Because the frequency is so low that there's. Okay, how many of you know how you hear actual sound? What is the mechanism in your ears? Okay, go ahead.
The sound waves, the compression of the air travels down through the ear, hits the tympanic membrane. When it pushes, it actually pushes through the fluid, and there are several little sets of bones which move, and the movement of that against something on the inside is how your brain will then.
Is it kind of like
Okay, you're pretty close.
Close.
pretty close. So the ear has an eardrum. Okay, so the eardrum is nothing more than a membrane to separate an internal pressure system from the external pressure system, so that it could actually move. Because otherwise, you cannot sense air pressure change without this kind of mechanism. So it attaches to the coil in your ear, which looks like a snail shell, and then inside the snail shell. So this actually will actuate the fluid. So the fluid inside will start to move, right? Because the eardrum is moving like this. So when it's attached to the snail shell, the fluid inside the snail shell would also move in accordingly. And what happens is inside the snail shell you have little hair-like extensions coming out of the snail shell, and depending on the position of where it is in the snail shell, they are sensitive to a different frequency. In other words, your ears is doing quote-unquote MP3 encoding by looking at the frequency domain and not really looking at the time domain as far as sound processing is concerned.
Well, and then also it's when you listen to really loud things, your first set of hairs are what are damaged first, and so that range is what you lose first.
And if I remember correctly, that's the high frequency portion. Yep. So you always lose the high frequency hearing first, and then the low frequency, which is all the way in, usually would be preserved for the most part over all the years. And that's why you hear, that's why they have cars where the bass can be heard over like 2 blocks away. But it takes a lot of juice to drive that much bass too. Yep, and it takes a lot of insulation so that the trunk itself does not rattle.
Takes a lot of rubber.
Rubber, how do you call those mats that you put into to line everything? So you have to make your car actually heavier in order to make it sound good. And then your alternator starts to burn out.
You got a stereo system, you can hear that. You hear the treble 2 blocks away.
Well, that's the reason why we do research in cold fusion, is to power up that amp. I just need a small cold fusion reactor in the trunk so I can hear the bass like 3 blocks away from my car.
No, you come. Yeah, the hatchback too, so it bounce all the sound waves off the back window. Just go right up.
You can bounce off the other cars too. The surround sound, experience, right, in a parking lot or when you're in heavy traffic, it will be kind of interesting when you have a stereo system that can actively see what other cars are around you and then project the sound to the other car, so when it bounces back to you, you have the perfect surround sound experience.
Sure,
It's
they
not
like
good
that.
enough to
Okay. So I'm giving you guys a whole lot of patentable ideas. Someone should run with that and get rich. All right. So we got graphics, we got sound. What else do you guys want to talk about? Okay, because everything really transduces eventually into numbers, into bits. Okay, characters is the only thing that is not exactly like that, because it's all discrete. It's like this symbol is different from this symbol, and they just need to have a different combination to represent. Yep.
Is gravity make any difference? Is gravity make any difference in our listening?
Gravity? In a way it does, because it changes the density of air, and when you change the density of air, certain characteristics will also change. Like if you listen to something underwater, it's all kind of different, because water for the most part is quote unquote not compressible, unlike air. All right, so I think we are all done with non-number representation. Time to move on to
Assembly language.
assembly programming, the actual programming part of this class.
I have one question on the
Yeah.
RGB. How does that alpha channel? I guess it's just another 8 bits.
Yeah, alpha channel is just another 8 bits for transparency.
Yeah.
So
I know
you
what
have.
it does. I just didn't-
Yeah, I think even in HTML you can specify
Yeah, you can-
RGB and alpha.
Yeah, you can say you have 4 channels.
Yep.
Well, well, if we could, for one second, I thought you said you would open up like a BNG file or PNG file.
I took a look at it. It's actually pretty complex, so I decided against it.
Okay. No problem. Well, you decided again.
Yep.
Okay,
I
that's gotta be
decided.
really complex.
Yeah, TIFF is easier, but TIFF is an older standard. The thing about PNG, which is portable network, graphics,
That's Microsoft's,
transmission,
right?
is it is designed to be friendly to network protocols. So if you have a transmission error somewhere within a huge PNG file, it is designed so that you can retransmit a chunk without having to retransmit everything. As a result, it makes the structure more complex because now you have to chop it down into chunks and make it recoverable quickly and easily.
Also has 4 channels.
It's also 4 channels. It's not just alpha too. You can also encode a gamma in it.
Oh, really?
Yep. Because different monitors have a different gamma correction.
Oh, that's
So.
So you could change, encode the color profile.
Yep. Yeah. So PNG is really a much more modern standard compared to GIF or JPEG. And that's why if you're working with any HTML documents and want to include graphics, you really should try your best to use PNG instead of GIF or JPEG.
You try to use whatever the smallest usually.
Say again?
So usually you try to use the smallest file size in HTML.
And PNG is pretty good too.
Depends on what you're doing.
As a lossless compression mechanism is actually pretty
If you
good.
have a big end, like a picture, you want to use
Right.
a JPEG, it's going to be 60 kilobytes and peak to 200.
Right.
So
Because JPEG is lossy, you can make it as small as you want. You just have to determine how much detail loss is acceptable for the website.
exactly.
Yep. But it's also a patented standard. So
But it
whenever
doesn't matter.
it doesn't really matter, but but philosophically speaking, it is a patented standard.
Yeah.
All right, so we are finally moving on to assembly language programming, which we have done a little bit already. Okay, we have done a little bit of this when we were using the toy processor, and you guys wrote the microcode, and we wrote a few instructions. You guys do remember some of that, right? That is machine code programming, when you have to specify all the zeros and ones, and you have to remember which combination of zeros and ones is loading the indirect register from one of the other registers. Which one is loading a register with a constant, which one is doing this, and which one is doing that. And you have to keep it all up here, okay? Which is not easy, but that's machine code programming, which is the basis of assembly language programming. So instead of having to memorize hundreds, not 4 or 5, okay, hundreds of binary code, each one 32-bit wide or worse, now you just have to remember what we call mnemonics, okay? They are basically a somewhat cryptic way to describe what a instruction does, okay? So we'll get started with this one. And we have useful GDB commands, and some of you may find this one useful. I have not ported in all of the notes from my other website, okay? So for the most part, I'm still in the process of doing this. And this is a really long one. It's supposed to be 11 hours. Actually, it would be even more than that to go over all of these topics, okay? So what I'll do is I'm going to import the topics from my previous class because I have all the materials done already for years. It's just that this is a new layout of cisp310, and I have not imported all the topics yet because I have to choose whether to import some of the older material or not. Okay. But these are the basic concepts that we have to go over. We have assembly language versus machine language programming, and the difference is when you're dealing with machine code programming, you're dealing with zeros and ones, okay, patterns of bits. When you're dealing with assembly language programming, you are dealing with mnemonics, okay, symbols, and you can leave a lot of the heavy-duty stuff, a lot of the heavy lifting to the assembler, so that you can focus on just the instructions and what you want the computer to do, as opposed to counting bytes, okay? As opposed to remembering, the binary bit patterns, as opposed to remembering which part of which opcode is specifying which register to do something, okay? Because otherwise, you'll have to remember all of that stuff. Tools, okay? The second topic, talks about tools. An assembler is basically the same thing as a C compiler, okay? It is not an interpreter, it is quote-unquote a compiler. In other words, what it does is it will do a one-shot translation from the source code into an object code file, just like with the C program. Okay? Now, how many people took cisp360 and understand the concept of a compiler versus a linker and so on. Okay, so the job of a compiler is actually done by an assembler in this class. It's basically the same concept, except the language itself is lower level, but it's the same concept. Okay. So for those of you who did not get the exposure because your professor told you that you should use code blocks or some other GUI tools, okay? So I'm going to go over this, just so that we are all now have the same knowledge of what is an assembler, what is a linker, and what is a debugger. Okay. So what you can do, okay, between the assembler and the linker, you can kind of think about when you write code, it is you're writing something, you're writing a novel in English, okay? But your target audience is Japanese. Okay, so are you getting that part? Okay, so you have two ways to do it. One way is to do a translation process, and the other way is to do it using interpretation. So you have an interpreter. The translation process goes, which is the usual way people go about doing it, is you would write up your cartoon or whatever, okay, and you would caption everything in English, and you would write volumes, okay, chapters, and then you bind chapters into a book, and then you go to a translator, okay, a translation service, and say, here's my book, I want you to translate this into Japanese so that I can sell it in the Japanese market. Okay? And that person will take your entire book in English and do the translation. It's a one-shot process. The output of the translator is the Japanese version of the same story, of the same images and whatnot, and now it can be understood by Japanese people. Is that okay? All right. Interpretation, which is done by interpreter or interpreted language, is a little bit different. Okay, in this case, you give the English version of the book to a Japanese person. But the Japanese person looks at the book and go like, I have no idea what this is about. So instead of using a translator to translate the book, you have an interpreter doing it. So for every page, every paragraph, you have a person sitting next to the reader and explain, oh, this means blah, 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 blah. That means blah, 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 blah. But you know what? If that person has to go back to a previous page, if the translation or the interpretation has to reoccur because it's done on a real-time basis. It's done on a on-demand, just-in-time basis, and that's interpretation. C and C++ are compiled languages, which means it's compiled one single time, which makes it more efficient. Assembly language is the same thing. Okay. So if the assembler is doing the same thing as a compiler, which is translating, why do we need a linker?
Files.
Okay.
Files you want together.
Multiple files, exactly. In your previous cisp360 projects, how many people have to use multiple files for a single homework assignment? Some of you.
400.
400, okay.
I think we did one.
For the most part, any project that you do, in college, in general, okay, will only be involving maybe 2,000 up to 4,000 lines of code. Okay, that would be kind of a bigger project already. And the necessity to break it up into multiple files is not really there. Okay, so unless the professor really wants to structure the assignment to make you break it up into multiple files, for the most part, it is still practical to use a single file that has like 3,000 or 4,000 lines of source code. It's still manageable. Okay? Which means, for the most part, when you are taking classes and you're writing, what you think is a complex program, compared to commercial programs, is really nothing. Okay? Because commercial programs easily would exceed hundreds of thousands of lines of code, easily. Okay? But then it doesn't make sense to put the entire program, hundreds of thousands of lines, into one single source file, does it? Now, give me a few reasons why that is not a good idea. Yep.
Like if you need to modify code, then you have to go through hundreds of thousands of lines of code to find exactly where you need to make the modification.
that is true, but Vim has bookmarks.
We can also reuse, like if you have,
Go ahead.
if you have a, something you probably could use again.
Exactly, that's a
Reuse it.
very good point. Okay, when you have one single source file, and within that source file you have, let's say you have 200 subroutines defined in that one single source file, of which 50 can be reused in this project, 40 can be reused in that project, and 100 of these can be reused in yet another project. That makes it kind of difficult to share code between projects, even though they do share, a certain part. And I can already see someone is thinking, copy, right? Just copy the whole file. Why is that not such a good idea? Using CP as make a copy of the original file and just modify it to fit the new other project. Why is that not really a good way to quote unquote share code?
Because if you update one file, it does not update the other file.
Absolutely. Okay, so so let's say you have like 20 bugs, in 20 of the subroutines, and you discover the bugs after the file was copied and modified in the other project. Okay, so now you have to fix not only the original file, but also every other file that you copy out of the original. And that's why in programming, at least in programming, every time you copy and paste, or every time you copy a file, you have to ask yourself, do I really have to do that? Is there a better way to do it? Okay.
It's also a lot quicker just to include. It's also a lot quicker just to do include.
Oh, abusing include, in a certain way. Yeah, yeah. A lot of people abuse pound include to include source code, which is not the right way of doing things.
I'm used to doing like PHP, and PHP to say include.
Right, PHP include is different from C
No, I
include.
know. I'm just saying. I'm saying you
But it's the
include.
same mechanism.
Same
You can
concept.
reuse code. Yep.
Yeah.
Yep. Go ahead.
So, what do you mean by abusing that? It's not the best way to throw the source in there.
Okay, so when you use a pound include in C and C++, okay, what is it doing? Okay, so let's say we have the pound include ABC dot H. Okay, what is it really doing?
Substituting whatever is inside of abc.h.
This is not the job of the compiler. Okay, interestingly, this is the job of a C preprocessor, otherwise known as CPP, which sometimes can be run as its own individual program. Okay, so CPP would go to abc.h, assuming that file does exist in the same folder. It will go ahead and grab the content of abc.h and make it appear as if it is in the file that has the pound include line. Okay, which sounds like a really good way to share code. Okay, so some people, okay, not knowing, the actual intention of pound include, would include the entire source file instead of the header file. Syntactically, there's no problem with this. The C preprocessor doesn't really care. Okay, if you want to pound include a .txt file, not a problem, it will do it. Okay? Because to the C preprocessor, it's just a file of this name, and make the content of that file as if it is a part of the including file. Okay? So the preprocessor doesn't care. The compiler will only care if it does not have C syntax, then it will complain about it. Okay? But you can include function definitions using pound include, as opposed to pound including only the prototype of a source file. Yep.
If you use that in whole file name there, will they use if we only like a few functions under this the file, will they compare run all the statements?
It is literally including the entire file as it is a part of this file.
They run all whole statements.
So if you are doing something like this, I got your hand, so I just need to finish this part. Okay. But remember your question. I'll get to your question next. So if you do something like this, abc.c, I know it doesn't look like that. abc.c here. Okay. So let's say abc.c has 500 subroutines defined. Okay, of which this program only needs 20. Okay. All 500 will be put in and compiled, even though they're not used. So this is not really a good idea to share code? Let me answer your question.
Well, I was just thinking of an example where like that can be problematic, like if abc.c had a main function in it, and you're including it with another program with its own main.
Yeah, you can do other things to make it work. You can use pound define, pound if def, pound end def, to make it work. But it does make a big, huge mess. Okay, so ideally speaking, when we are dealing with source files in C and C++, the smaller the file, the better, because it will give you a finer granularity when it comes to sharing code. So instead of having to share, a huge file that has 500 things in it, because you just want to use 20 of those things, if you break it up, and those 20 things is in its own smaller file, it's better because now you can hand pick and say, oh, I just want to include this, this, and this, and this. Okay. So at this point, I just want to establish why it is useful to break a big program into multiple source files. Okay, each source file is one .cpp file basically. Okay, from the previous class. Yep.
Can we create like a user function, and which is different from system function library, and we can share, which is only for user side. Do you see?
Can we create a
function called a user function?
User function?
Which means we only can call, which is the user like a program level, which is not from system level, which is different from the system library. Can we do that in C?
So you want something that only a user program can access, but not a system program.
Yeah, which means we only give when they allow the program to call that, but it's different from the system function.
But why would you want to do something like that?
Which is only share this library for a certain level of the program. Since they can run it.
You can accomplish that by using some other mechanisms that a modern operating system can support, like group permissions and stuff like that. Yeah, but that's kind of out of scope for as far as our discussion is concerned. Okay, but the point is you have multiple source files. Okay, and it's not a good idea to use pound include to include those multiple source files. Well, then what do? Well, each source file needs to have its own translation process, right? It's kind of like writing a graphics novel that has multiple chapters. Okay, so each chapter is its own little unit, another chapter is a different unit, and so on and so forth. So the translation process, the translator, okay, the compiler in this case, will only take one chapter at a time and translate that into the translated chapter. It will take another chapter, translate it to the third chapter, and translate it, and so on. That's not a problem, okay? The problem is, what if the chapters have references outside of the content of the chapter itself?
The moment you jump over there to look at it, you're going to have to translate.
Okay. So, are there any examples that you guys can think of, when you're translating a document that a particular chapter may have something that it's referring to that is not within the same chapter? Footnotes. It might want to say, if you're dealing with like a manga or something like that, it might have a little reminder, right? To get it, to remind yourself of what this character is about. Go to page blah 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 blah. Okay, just a page number. Okay, it's fairly normal that in a talk document we might have links like that and go to a certain page number for details or more information about this. Okay, but the page number is going to change, isn't it? Because when you're writing something in English as opposed to the translated version in Japanese, the number of pages that it takes for a certain chapter can certainly change. Okay, it makes sense, right? So now in the English version, you have one little thing that says refer to page XYZ for the definition of a particular word. Okay, it's in the chapter, but you don't even know the page number until you have compiled the entire book. Is that making any sense? Because when you only have individual chapters, you can see that, oh, this definition is on page 19 of this chapter. This definition is on page 67 of this chapter. But what is the absolute page number once you bind all the chapters together? I don't know, because I'm just translating one chapter at a time. Is that making any sense? So any references out of a chapter cannot be resolved until you're binding the entire book. So the compiler is going to leave little text, it will leave little post-its onto the translated version, and it will say, oh, on this page, there's an unresolved reference that I need to come back and fix once we bind everything into a single book. So it will have a lot of little tabs like that along the side of the translated individual chapters. The linker is not a translator. The linker is basically just putting everything into one single book. It's binding all the chapters into a single book. Okay, and the linker's job, there are several jobs that the linker has to do. One is just physically piling the chapters on top of each other. Okay, that's one job of the linker. But the second one is to resolve all of these references. Because once you have all the chapters bound into one single book, then you can renumber the pages. So it's contiguous from page 1 all the way down to the last page of the book. Once you have the absolute page numbers, now you can go back and look at all those little post-its that the compiler, the translator, has left behind, and go like, oh, okay, from here, this is an empty page number that needs to be filled in, and it needs to refer to the page number when that thing is defined. Are we still doing okay so far with that analogy? That's the job of a linker. So that's why compiling is not enough to give you programs that can execute. You need a linker to also finish up the binding, resolving the unresolved references, and also including any type of extra code that is not even a part of your program. Printf, cout, okay? All of those things are in what we call a library. So the linker also now needs to look at those things and go like, oh, okay, cout is not defined in this program, but I think I know which library has the definition of the streams and cout, and go to that library and check, oh, okay, here's a chunk of code that I can pull and put into the book. Here's another chunk of code and put into your book, and so on. So the linker is going through all of these steps to make sure that you end up with what we call an executable file. Now, an executable file, as the name implies, is executable, okay? You can actually run it at that time. Okay. So that's why we have this process. We have an assembler, which is the translator. And the interesting thing is you can actually link object files that are created by different translators. You can have one object file created by C, one object file created in C++, one object file that is created by assembly, by the assembler, and yet another one by Fortran compiler. And the linker doesn't care. The linker is, because by the time you get to the linker, they're all in object file format already. They're all in Japanese already. So whether the original one is in German, Spanish, American English as opposed to British English or whatnot, doesn't matter, because by the time you get to the linker, it's already in Japanese. Is that okay so far? So the linker has a very interesting and important role when you are developing programs. In this class at least, okay, I will also emphasize the use of a debugger, okay? I don't think we have used the debugger a whole lot up to this point because we haven't really written a lot of programs that require the use of a debugger. And I don't really care about what your C++ professor has to say about the debugger. Because some of you may have heard from certain professors that you should not be using a debugger is not worth the time to learn, and so on and so forth. That is, everybody is entitled to his or her opinion. Okay, but in this class, I am entitled to my opinion. And I think a debugger is a very essential tool that you should learn to use. Not only because you want to pass this class, but also because it's a useful tool for your other programming classes and also on the job. Okay? If you can illustrate to a potential employer that you can utilize a debugger, efficiently in order to locate bugs and stuff like that, I think it would not hurt, okay, your application. In some cases, it might help, okay, because some employers may value employees who know how to use tools effectively, and a debugger is a tool like that. A debugger, if you think about it, okay, if you think about debugging a program as a medical doctor's job to diagnose disease or illness or something that is wrong with a person, a debugger is analogous to an X-ray machine, ultrasound machine, and stuff like that. So it allows you to see things that is not obvious from the surface. Okay? And that's why it is a very useful tool, because would you go to a doctor, a medical doctor, and you're coughing like there's no tomorrow, you suspect that you might have tuberculosis or something like that, and then the doctor is just kind of like, let me just put a stethoscope on you. And even that is kind of like a debugger too. So the doctor would just go like, cough a few times so I can hear how you're coughing. How long have you been coughing? Okay, I think this is just a normal code, left over from a normal code, but I have been having this for a whole year. Well, from what I can tell, just listening to the symptoms and stuff like that, I think it's just a normal code. But don't you have an X-ray machine or something that can just see through my lung and see if it is tuberculosis? Oh, I don't trust X-ray machines. My mentor said X-ray machines are overrated. They're difficult to operate. I don't want to use an X-ray machine. It's kind of like that. Okay, so this is as gently as I can put it.
Prolonged exposure to X-ray machines are.
But so is tuberculosis. All right. So those are the tools, and we will definitely emphasize the use of a debugger in this class, because I think if you learn how to use a debugger or use the tools offered by a debugger effectively, it will help all of your programming classes and also on the job as well. Okay. Now you may not want to use GDB on the job because some people do not like the command line interface, but the concept of using a debugger stays pretty much the same. All right, so we will now focus on basic syntax, and we'll start to do some actual program in this class. Okay. All right, so we'll go ahead and start. Well, we have 8 minutes here, so we can do some kind of interesting stuff. So we'll go ahead and start with something that we are familiar with. In other words, these are mirrors to instructions that we have already implemented using our architecture. Okay, so we'll start with things that we are familiar with. And we'll go ahead and say load register, okay? Because I'm hoping some of you still remember the instruction that loads a constant into a particular register, okay? And the program goes like this, okay? .text, okay? Now these are called directives. .text is a directive, which means it does not actually end up as an instruction in the object code. This is instruction to the translator itself. It is not content to be translated. Okay, is that clear? Does everybody understand what I just said? It is instruction to the translator, but it is not content to be translated. Yep, go ahead.
So it's sort of like if we're going back to the book analogy, you telling your translator something specific about your book that is not going in the book, but something that you want them to know. Right.
So you might want to say something like, like the English word cool, okay, has a lot of different meanings. And actually, the cool guy, in the cool guy context, that cool, use of cool, is actually absent in many languages. Okay, there's no direct translation into other languages. So you might want to leave a note to the translator and say, just go find the closest meaning to this, to cool in this context, because you know ahead of time that this might be a difficult word to translate. So that one little note that you leave behind to the translator does not appear in the published book in Japanese, because it is just instruction or special note to the translator himself or herself, but it doesn't actually get into the content of the note. Are we doing okay so far? And in this context, it's called a directive. Okay, a directive is note to the translator. So dot text is just a special note to the translator. We'll talk about this in just a little bit because I want to at least get to a little bit of coding here. Okay. So is dot global underscore start. It exports a label called underscore start, which has specific meaning to the linker itself this time. And underscore start colon is basically a quote unquote C syntax. It is defining a label, a symbolic label, which is a symbolic name for a certain location in a program. Okay, so if I want to refer to this location, I can just say, oh, underscore start. That's the name of this location. So instead of remembering locations like 10 in hexadecimal, 25 in hexadecimal, we can now remember just symbolic names, which are far easier to deal with compared to absolute numbers. And I'm just going to use one instruction here. Okay, move L, which is move long. Now you don't have to memorize everything. I will import the proper sections from the previous class so that we'll have references to these things. So move long $24 into %EAX. $24 is a constant of 24, okay? And EAX is the name of a register. So in the processor that I designed, we had register ABCD. In the Intel processor, we have registers EAX, EBX, ECX, and EDX. Now the reason why they are not just register ABCD is because E stands for enhanced mode. A is not really just A. Okay, ABCD is not what you think. It's not really just the first four letters of the alphabet. A is accumulator, B is base, C is counter, and then D is not remember. It's not the incrementer.
Is it like the indirect?
It's an indirect kind of thing, but I cannot remember the full name of D. But each one actually has a special name. It's not just because they are the first four letters of the alphabet. So I'm going to put it into the register, and that's it. That's my entire program. Okay, and I will also specify a no op here, just so that I can stop at the no op instruction. I'm not going to tell you how to end this program properly today, because that will take that will take another trip. Okay. So no op is just one more instruction, so I can stop at that instruction, and so that I can examine the content of EAX after the instruction, after the move long instruction.
Like a breakpoint?
Yeah, so I can put a breakpoint. I have a place to put a breakpoint. Okay. Now no op, interestingly, corresponds to opcode 00 in our architecture, our simplified architecture. Can someone tell me what opcode 00 does? It's a fetch cycle, okay, but what exactly does it do? Does it do anything to the ALU, the registers, the indirect register, or memory content?
The zeros and all that.
Absolutely nothing, right? It increments the program counter, so you'll be ready for the next instruction, but by itself, opcode 00 doesn't do a single thing, okay? It has no effect whatsoever on the registers, nor the ALU, doesn't write anything to memory. It just prepares the PC, the program counter, for the next instruction. So for the most part, it is as if it is not there, okay? And we call that no op here, no operation, which boils down to the same thing. And the other interesting thing about no op is, this is the mnemonic, okay? Remember, a mnemonic is a cryptic way to describe an instruction, an opcode. The actual binary code of no op is 0.
A single zero?
Yep, 00, a single byte.
Does that have a tab? Do you have a tab after start?
No, that's actually optional. It's just 2 spaces here. Yeah, but that's optional. You don't need to have the space. I just prefer to have the space. Okay, so this is my first program, and we'll just go ahead and save the file. Okay, this is just a text file. So for those of you who want to use Windows Notepad or whatever to do the editing, you can do that, and then just use WinSCP to transfer the file over to the other side. Well, I mean, it's a personal choice. You guys can make that choice. Okay, so now that I have this file, I'll do ls just to make sure that it is here. Okay, this is my source file. The first thing I have to do is to compile it. Okay, and the compiler is called AS, which stands for assembler. -g stabs, which means I want to include debug information, so the GDB has references back to the source code later on, and then I specify the output of the assembler as ldreg.o, which is a convention, okay? You can call it anything you want. The object file name, the object code file name can be anything in this case, okay? But the convention is a .o in Linux to mean it is an object code file. And then we have to specify the source file, which is ldreg.s. And it does not complain about anything, so syntactically everything is good, okay? So now we have one single translated chapter, okay? But it's not an executable just yet, okay? The object code actually contains binary code of the instructions already, but it's not ready to be executed. It's just like, you know, with a single chapter of a book, the book is not ready to be published. You don't want to publish one single chapter instead of a whole book, okay? So it's the same thing here. So to, yes?
Why do we have to create this file .s?
I just did it using the editor.
Why do we have to use .s or other type of?
It is conventional to use .s, so I suggest that you follow the convention. Because if you don't follow the convention now, later on in the class, there will be things where the convention becomes important, then you might run into problems. Yep.
So, like if you're, like if somebody chooses to like write it in Windows in a text and then import it over, it's just like setting it as .s will work for importing it over now.
Correct, but you have to be careful because Windows is case insensitive when it comes to file names. So you have to make sure that it is lowercase s and not uppercase s because they are slightly different. Okay, so the next step is to do the linking. Okay, LD is the name of the linker program, and -o ldreg means, you know, the output, which is the executable, is named ldreg with no extension. Unlike Windows, who wants to use .exe as an extension of an executable, in Linux, once again, the extension is useless, okay? So the convention is you do not use an extension for an executable file. The input to the linker is only one chapter. We only got one chapter here, which is ldreg, okay? So the output of this, if I take a look here, we have ldreg.s, which is the source code, ldreg.o, which is the object file. This is the translated chapter, but it's not a book just yet. And then we have ldreg, which is the book. This is the executable. So those are the three files that we have at this point. The one that you can actually run is ldreg. So to run this program, I can just run it on the command line, but it will crash because I don't have the proper execute this program. So the only way to run it, quote unquote, properly is to go through GDB. GDB is the debugger in Linux. So when you do this, it will give you a whole bunch of messages. You can type L to list the program. And since we have a pretty simple, short program, this is all that there is. You can use B5 in this case to put a breakpoint on line 5. Okay? All of these commands I would use like again and again and again in this class. Okay, so you will get repeated exposure. But if you want to, you know, re-watch this video and just kind of jot down some notes and say, oh, B is to set a breakpoint, and you use a line number and stuff like that, it will help you because, you know, by the time that you have to use GDB to write to debug a program, then you will know you have a reference to, you know, go back to those commands.
Will it execute the code at line 5 or will it stop?
It will stop right before it executes line 5. So the breakpoint is technically before line 5, right before. Okay, so we'll set the breakpoint, and then we'll run the program with R. Okay, so R is the abbreviation of run, and you know, it starts the execution of the program. And obviously, it stops on line 5 because I put a breakpoint over there. Okay, if I did not put a breakpoint on line 5, then it would have gone through line 5. But since this program does not have the proper execute, it will crash. It will give you a segmentation fault. You know, when that happens. But what I do want to know now is to say, oh, okay, I think we just put a constant of 24 into register EAX. Can I see that? Can I confirm it? And the answer is yes, and there are different ways to do it. One is to print $EAX. In other words, when you try to print the content or the value of a register, you have to precede the name of the register, EAX in this case, with a $sign, because it is a quote-unquote special variable that is understood by the compiler, by the debugger. There's another way to do it. You can also do IR EAX, and I R stands for info register, okay? So we're displaying information about registers, in this case, particularly EAX. And it will show EAX in both base 16, which is 1/8. It has a 0x prefix to it. That means it's a hexadecimal number. It's also shown as a base 10 number as 24. Okay? So this is as far as I wanted to take it in today's class, okay? Just to introduce the basics of writing a program in assembly. And this is an instruction that we have dealt with, okay? We just didn't call it a move long instruction in the processor architecture that we played with. Yep.
Is that 24? Is it the door 24?
Is it what?
24. EAX 24.
This is the base 16 value.
Yeah.
This is the base 10 value.
Yeah, which is 24. The value is 24. Is that right?
Say again?
Which means that the value is 24.
Which means register EAX has a bit pattern that represents the value 24.
So is that mean same as the dollar 24?
It's the same as
Dollar 24.
$24?
Mm-hmm.
No.
Then
Where does that dollar 24 go?
There's no $24.
They
Oh,
command. They
no, I think
command
you're
them
talking
all.
about when you said you were going to
dollar
pass a
24.
constant 24 into it.
Yeah.
That's the syntax to specify a parameter to load into register 24.
Yeah, so that's-
because move long without a $24 means something entirely different. So we are not moving $24 into EAX.
Oh man.
All right.
And normally don't you move
So
people
I'm
out?
going to end the lecture here, and in about 10 minutes or so, I'll go to the lab, and we'll take a look at the program that was due today, and I will basically go develop the whole program using the next 1 hour and a half or so. There's no homework assignment yet, okay? So you guys can take a break so I can catch up.
You're also going to record yourself.